Now we are going to a minimal spanning tree. At this point, we are not going to consider the weighted graph. The weighted graph. Now, as we are moving along the vertices, we want to get the minimum distance that you can move, or the shortest path that you can take to go through all the vertices. So for the minimum spanning tree, then we have to deal with the weighted graph. So let's consider the weighted graph J with n number of vertices. In this case, all the possible spanning tree level n minus 1. You know why it is n minus 1. If you have n vertices, then at the end of it, or the spanning tree must get n minus 1 edges. The idea is to find the spanning tree with the least or the minimum weight. With the least or the minimum weight. So it means that we just move through all of them. We have so many ways that we can get to all the vertices. So many ways. But I want to get the least among them. And that one now becomes the minimum spanning weight. So the algorithm that we are now going to consider here will be the Kruskal and the Crane's algorithm. So we have the Kruskal and the Crane's algorithm that we are going to consider. We have a lot of them. But we are not going to consider only these two. Okay, so let's start with the first one, the Kruskal. Now the input that just we have the connected weighted graph J. Then the idea is that maintaining an acyclic subgraph of J, enlarge it with an adjacent edge with the least weight to form the spanning tree. Now let's consider the edges in ascending order of weight. So the steps are 1. Arrange the edges of the J in order of increasing weight and select the edge with the minimum weight. Now proceed sequentially. Add each edge which does not result in a cycle until n minus 1 edge are selected. Now third one, exit. If you're able to do that, then you have to stop the process. So now let's apply these steps to the graph here. Now, if you're going to consider the minimum spanning weight, what we are not going to do is that we are not going to look through all the edges. Now you have the weights on top of them. So we are now picking the least among them, and we start from that edge. So look at this graph. Now the least edge now is 4. The weight here is 4. That's the least among all the weights. So to the length of BD is 4. Then we are not going to start from the edge BD. So BD, we have the BD here. Now from the BD, the end of BD, we look out for the adjacent vertices to all of them and pick the least weight among them and join it to the edge BD. So if you are here, we have the weight are 12 here, 11, 7. That for B. Now for D, we have 5. So among all of them, we have 12, we have 11, we have 7, we have 5. Which are the least among them? It's 5. So to me, if you move from B, D, I must go to D, F. So we have this. And then we are now here. So we are now at 5, F here, BF. Now BF is also adjacent to A, B. You have A here, you have B also here. Now you can see that 7 is the least among 7 and 11. But if you take 7, we get to B, and we have formed a cycle. We have formed a closed figure. We have B, DFB, which is close figure. We don't get that one. So to me, we can't take 7, even though the least among them. We must now fall to go to A. Therefore, we have to take A as what? That we will pick this edge. AF. So we are now at A. At A here, we have adjacent as C and E. But AC is 9, AE is 5. So the least among them is 5. Therefore, we must move from A to E. So we pick this edge at that. Then at E, we have only one vertex to go, which is C. So it means we must go to C and pick this edge EC or C. Now we are able to move through all the vertices. Hence, we are done with our process. Are you okay? So now we are not going to get the spanning tree. The spanning tree now will be those edges that are marked. So we are removing the chords from the graph. Then to get the minimum spanning weight, we add all the weights on those edges that we have used to get the minimum spanning weight. Okay. So we are not going to remove all the edges that are not used from it to get the spanning tree. And we are going to arrange these used edges in order of magnitude on the ascending order. Then we add all that weight that we have used to get the minimum weight for the spanning tree. So let's go to what we have here. So this is what we have got. So now we have just ordered this weight. We have BD at 4, 5, 5, 8, 11. And here BD, DF, AE, EC, AF or FA. And these are their weights. Therefore, the minimum spanning weight or the weight of minimum spanning tree, now I just summed all of them up. And that will give you a 33. So it means the least path that you can take by going through all the vertices is 33. And this now become the minimum spanning tree. The minimum spanning tree. Is that point okay? So at issue here we have how many vertices? We have 6 vertices. Therefore, we might get it 5 edges. That's the n minus 1 edges. So we have 1, 2, 3, 4, 5. Therefore, we are right. And this will give you the minimum spanning tree going by the Kruskal algorithm. Now the prince may give us even different weight. But per the Kruskal algorithm, this one has become the minimum, the least among them. As for this one, no matter what, we cannot get different shape. Unlike the BFS and the DFS also. This one, the minimum is minimum. But I tell you, may get, you may get even a different shape depending upon, you may get even a tie. You have to break a tie. Breaking a tie means where you are now about 2 or more edges are having the same weight. Then you can break a tie. When the tie comes in, then you may get a different shape. I hope you are getting my point. So when you have a tie to be broken, then you can get a different shape. But if there's no tie there, then you get the same shape and then the same amount. Okay, let's see another example. you have a weighted graph like this. So about the Kruskal spanning tree, where should you start from? Let's go through all to check for all the leaves among all of them. And it's 3 here. The leaf weight is 3 here. Therefore, we are now starting from the edge 2, 3. So we can use this edge 2, 3 here. Now, at the end of the edge 2, 3, we have at the ends of the edge 2, 3 here, we have the 3 here with the adjacent vertices being 8, 4, and you have the weight 8, 8. Now, when you go to 2, we have 7, we have 8, we have 6. So among all of them, we have 7, 6, 8, 7, 8, 8. So the least among them is 6. Therefore, we must continue from 2 here to 7. So we pick this weight. So we're now having 2, 7 here. Therefore, we are at 7. Don't forget, we are now continuing from 7. So at 7, we have 4 here. We have 5 here. That's the adjacent edges. So the least among them is 4. Therefore, we now go to 1. So by picking this edge with the least weight. So we now get to 1. So at 1, we are now having the adjacent edges as so the adjacent edges now are 5. The weights are 5, 9, 7. 4 is already used, so we are 7, 5, 9. But if we take the least among them is even 5. So we will now go towards 6. We will now pick the egg this. That is 1, 6. So we are now at 6 here. Now at 6, we have only 1 egg to go with 4. So we take this root. We get to 5 here. Now at 5, we can go to 1. We can go to 7. We can go to 2. They are all being used. Therefore, we will either have 8 and 4 to go to vertices 8 and 4. So among them, the least among them is 4 because there is 4, there is 5. So we have only 4 to go here. We can't take this, so the least one is 4. Therefore, let's take this edge. So we are now at 8. So at 8, now you can't go to 2, you can't go to 3. So you only go to what 4. Then we'll pick this root. Now you're now at 4. At 4, don't forget that 3 is already been used. Therefore, we can't go there again. So we are done with our movement. Therefore, we arrange the vertices in ascending order. And then remove the chords from the graph to get the spanning tree. So this is what we're going to get for that. And then the minimum weight for the spanning tree now will be the summation of all the weights on the edges that we will use. And we get it to go 32 as our minimum weight for the spanning tree. And this one now becomes the spanning tree. I hope everybody now getting the Kruskal way. Good. Any question? Any question before we go to the claims? Any question? Good. If no question, then you can move on to the last algorithm to determine the minimum spanning weight. And that was the Prim's algorithm. The Prim's algorithm.